Hello class, welcome to the second module on CHM 312, Physical and Structural Chemistry 2. Today we'll be looking at dipole moment 2. Last class we started looking at dipole moment and we explained that dipole moment arises from a difference in electronegativity. And one very important point that I also mentioned last class was that if the shape of the molecule is symmetrical, the dipole moment will be zero, even though it has bond dipole moment. The overall dipole moment will be zero because they will cancel each other out. And I cited some examples of symmetrical shapes, say linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. These are linear shapes. These are symmetrical shapes. And as such, any molecule having this kind of shapes will not have a net dipole moment. But we have bond dipole moments, but the net dipole moment will be zero because we'll cancel each other out. Now let's see some examples to buttress that statement. Firstly, you should know dipole moment can provide information about the geometry of a molecular structure. So if I see a molecule, even if I don't know the structure of the molecule, once I know the dipole moment, I can predict the molecular geometry of that particular molecule. If there are two or more possible structures for a molecule, the correct structure can be determined by the study of its dipole moment. Let's see what I'm talking about. Example 1, we have water. H2O has a bent structure. How did I come to this conclusion? Of course, we can come to this conclusion by knowing the valence bond, valence shell electron repulsion theory, VSEP, or by valence bond theory. We can use that to know the shape of water, whether water is linear or bent. But I can also use by dipole moment to come to this conclusion. So how do we use dipole moment to come to the conclusion that water has a bent structure? The possibility of water having a linear structure is very high because as we can see in water, water has a structure that is very similar to what we see in CO2. See CO2 has your carbon, double bond oxygen, which I showed you in the last class, double bond oxygen. So you can see the shape are very similar. They have a structural backbone that we call AX2. Structural backbone of AX2 is AX2, meaning that we have a central atom that is attached to two different constituents. This is the central atom, this is our A, and this is our X2, this is our A, and this is our X2. But in CO2, the shape of CO2 is linear. CO2 has a linear shape. CO2 has a linear shape. But in the case of water, the shape of water is not linear. So how come water is not linear? How can I know what the shape of water is through its dipole moment? That's simple. Now, if water was to be linear, look at the linear shape of water. If water was supposed to be linear, what is supposed to happen to the dipole moment? Since the hydrogen here will be carrying which one will be carrying the positive charge? Is it the hydrogen or the oxygen? I told you the one with the higher electronegativity will be carrying the negative charge, and oxygen has a higher electronegativity than hydrogen. So oxygen here will be carrying the negative charge. So here, oxygen, we are going to have a partial negative charge, and then on the hydrogens, we have partial positive charge because oxygen is more electronegative than hydrogen. Now, it means the arrow will be facing the oxygen in both directions. Is that not so? Because I told you the arrow moved towards the negative charge, and in the positive end, we use a cross tail to represent the positive end. So it means the oxygen here will be negative, and then the two hydrogens are the partially positive charges. Now, if you see this shape is a linear shape and it is symmetrical. The implication of this is that if water is linear, the net dipole moment would be zero, because the dipole moment of this end will cancel out the dipole moment of this end. Don't forget, I've already said that before. There will be bond dipole moments. Let's say the bond dipole moment might be something, let's say a total of 3. That means by the time we subtract the electronegativity difference, and then we use it to calculate for the bond dipole moment, we might get 3 using the formula I've given you earlier. And on this end, of course, you must also get the same thing. But since they are moving in opposite direction, if this is +3, this would be -3. And +3 minus 3 is equals to 0. So therefore, the net dipole moment will cancel each other out. Now, it means if water was to be linear, then the net dipole moment should be 0. Now, let's consider water having a bent shape. If water had a bent shape, the net dipole moment will not be 0 because, of course, you can see that the two of them, instead of them to cancel each other out like we have here, they will sum up. They will sum up. This will come to this, and then both of them will sum up to form this third force. So it means instead of canceling each other out, they will sum up. So if this was 3, 3, instead of us having +3 minus 3, both of them will be having +3 plus 3, and then it will become 6, or -3 minus 3, and it become -6. So the value, the net dipole moment will not be 0 in the case of a bent water. So if water is bent, the bond dipole moment will add vectorially to give a definite net dipole moment. Now, since water actually has a dipole moment 1.85 dB, which means we've calculated it experimentally and we see that the dipole moment of water is not 0, its linear structure is ruled out. Thus, water has a bent structure as shown in B. So by knowing that the dipole moment of water is not 0, automatically I am sure that water will not have a linear shape. So peradventure, if I ask you that I tell you that the dipole moment of water is 1.85 dB, which has been given here. 1.85 dB is the dipole moment of water. I tell you, justify that the shape of water is bent. Simple. All you need to tell me is if the shape of water was to be linear, then the dipole moment should be 0 because they will cancel each other out. So water has to be bent in order for it to have a dipole moment greater than 0. Okay, let's see another example. If we have CO2, CO2 has a linear structure while SO2 has a bent structure. I told you already earlier that CO2 has a linear structure. But in the case of SO2, SO2 has a bent structure. SO2 has a bent structure. So how do we justify this? If the same thing as water, I could have asked you to justify the shape of CO2. Will the shape of CO2 be bent or linear? How do I justify it? If I tell you that CO2 has a dipole moment of 0, automatically you should know that CO2 will be linear and not bent, because for it to have a 0 dipole moment, it means that the only possible molecular structure for it is linear. And as such, the dipole moment of each of the C double bond O, C double bond O, C double bond O, the dipole moment cancel each other out. That's why we have 0. If I ask you the same question for SO2, which is also similar to CO2, but is not having the same shape, if I tell you that SO2 has a dipole moment of 1.63 dB, justify that SO2 is not linear or that SO2 is bent. Either way, you are going to tell me that yes, SO2 cannot be linear, because if it is linear, then the molecules will cancel, the bond dipole moment will cancel each other out, and you have a net dipole moment of 0. But since the SO2 has a dipole moment greater than 0, it means that it cannot be linear, and thus it has a bent structure. BF3 has a planar and NH3 has a pyramid structure. Now, both of them are also similar. You can see I'm comparing similar molecules. The molecular backbone of this is AX3. Molecular backbone of this is also AX3, but their shapes are not the same. How can we justify that using dipole moment? For the case of boron trifluoride, it will have a net dipole moment of 0. Once you know the net dipole moment is 0, then it means BF3 has a symmetrical structure. And because it has an AX3 molecular backbone, then the structure will actually be a trigonal planar. It has a trigonal planar structure. And the dipole moment of boron trifluoride is 0. The bond moment of the 3 BF bonds cancel each other's effect, and the net dipole moment is 0. So that is why the structure will actually be a trigonal planar. But in the case of ammonia will not have a planar structure. Ammonia will be pyramid in structure. Why? Because the net dipole moment is not 0. The net dipole moment is 1.47 dB. This has been calculated experimentally. So it means that if it were to be 0, it ought to have the same planar shape like BF3, but instead it has a pyramidal shape. And that's what I've explained here. I said ammonia has a dipole moment 1.47 dBi. The 3 hydrogen atoms lie in one plane symmetrically with nitrogen atom at the apex of the regular pyramid. The dipole moment of the 3 hydrogen bonds on vector addition contribute to the net dipole moment. In addition, there is a lone pair of electrons on the nitrogen atom. Since it has no atom attached to it to neutralize its negative charge, the lone pair has a large contribution to the net dipole moment. Thus, the overall dipole moment of ammonia molecule is the resultant of the bond dipole moment of the NH, the 3 NH bonds, that is 1, 2, 3, and then that of the lone pair. So it means ammonia has a lone pair, and this lone pair also will contribute to the net dipole moment. Since it does not have any atom to neutralize its negative charge, the dipole moment contribution of the lone pair is always high. That's why any molecule that has a high dipole moment is most likely to have a lone pair. For a molecule to have high dipole moment, it means it will most likely have a lone pair. That means a non-bonding pair of electrons that is on the central atom. So that is what we have here. So let's see methane. Methane has a tetrahedral structure. Of course, we can justify the fact that methane has a tetrahedral structure. Methane, which is CH3, has 0 dipole moment, despite the fact that each of the CH bonds has a bond dipole moment of 0.4. Each of these bonds have bond dipole moment of 0.4. This can be explained if the molecule has a symmetrical tetrahedral shape. So automatically, once I see CH4, I can predict the shape will be tetrahedral because in the net dipole moment of CH4, that is methane, is 0. So the only reason why it can have 0 dipole moment is if the shape is a symmetrical tetrahedral shape. Each CH bond in the pyramid CH3 group contributes 1/3 mu into bracket mu cos 70.5 to the resultant dipole moment. You don't need to memorize this, but what we are trying to say is that all these 3 here, they form a pyramid. This CH3, you know this is CH4, but the CH3, that is all this. Okay, let me highlight it so that it can be clearer. All of them here. Yes, so this is the CH3, the pyramid CH3. Each of them together, they contribute a 1/3 mu into bracket mu cos 70.5 to the resultant dipole moment. Thus, the net dipole moment of CH3 group is equal to mu. This acts in a direction opposite to the 4th CH bond. That is, all these 3 are moving in the same direction as you can see, but they act opposite to this 4th one. This is another one. This is another bond of CH. This is the 4th one. So they are acting opposite to the 4th bond, which is also equals to mu, and therefore they will cancel each other out. So this one cancels out the remaining 3 that are coming. So that is how that's how we are able to come to a conclusion that CH3 is going to have a net dipole moment of 0. That's CH4. Now, identification of cis and trans isomer. We can use dipole moment to identify cis trans isomers. So the cis isomer has a definite dipole moment, while the trans has no dipole moment. So I can identify the cis and the trans isomer of a molecule just by calculating its dipole moment. What do I mean? Is that if I have this molecule here, this molecule we have here is a dichloroethylene. You can see 2 chlorides, so that's what we call a dichloro, and these are 2 carbons, ethylene double bond, and this here is also a dichloroethylene. What's their difference? They are actually isomers of each other, but they are what we call geometric isomers of each other. Since one of them is cis and the other is trans. How do I know cis? You can see the 2 hydrogens are in the same direction, so we call them cis. Look at the 2 hydrogens, they are facing up. Here we have 1 hydrogen facing up, 1 hydrogen facing down, so we call that trans. Now, for the cis isomer, the dipole moment will not be equal to 0 because you can see the 2 hydrogen are going to be moving in this direction towards the central carbon, while the 2 chlorine are moving in this direction. They can't cancel each other out because they are not the same. So definitely it will have a net dipole moment greater than 0. But for the trans here, you can see the hydrogens are going to be facing each other, meaning that this hydrogen will cancel out this hydrogen, this chlorine will cancel out this chlorine, and it will have 0. So if I have two isomers and I want to distinguish between the cis and the trans, all I need to do is calculate the dipole moment. The one with the dipole moment of 0 will definitely be the trans, while the one with the dipole moment greater than 0 will be the cis, because the trans is symmetrical while the cis is not symmetrical. So this is one of the ways in which I can ask you to explain some concepts in dipole moment. Also, we can identify ortho-metal para isomers of the benzene ring. A benzene itself has a dipole moment of 0, thus it has a planar regular hexagon. So benzene on its own without any substituent is a planar regular hexagon. Therefore, they will cancel each other out and the net dipole moment of benzene will be 0. But in general, when we have a para disubstituted benzene, it has 0 dipole moment, while that of the ortho isomer is higher than the meta isomer. Let's see what I'm trying to say. What do we mean by a para substituted, and what do we mean by ortho or a meta substituted? Look at this. This on a benzene ring, when you have a substituent on this carbon of the benzene, that is the carbon here, we call this a para substitution. Then the next one, we call it ortho. The next one, we call it meta. The next one, we call it para. So this is para, ortho, meta, para. Para up here, ortho, meta, para. So the one here now will be the same to be the one here. If this is meta, this will also be meta. If this is ortho, this will also be ortho. So that is how we name the various carbons in benzene. So now when we have a para disubstituted benzene, it will have 0 dipole moment. Look at it. This is a para disubstituted. You can see this is para. This chlorine here is in para. This chlorine here is also in the para position. So the net dipole moment will be 0. And it's obvious because this will be symmetrical, just like the normal benzene that also has a 0 dipole moment. It will still be symmetrical, meaning that this end will also cancel out this end. But when we have a meta substituted, this is a meta substituted here. This is your para, a fixed position. Now this is your para and this is your ortho and this is meta. So we'll call this one a meta substituted isomer. So this is a meta disubstituted isomer of the benzene. Disubstituted means that two hydrogen have been removed to be substituted with another atom, in this case chlorine. So we have one in the para, we have one in the meta. So we'll call this one the meta isomer. You can see the meta isomer has 1.5 dBi, while for the ortho isomer, which is this ortho isomer of the disubstituted benzene, has 2.6. So it means the ortho isomer will always have a higher dipole moment than the meta, while the para will have 0 dipole moment. That's a very important statement. If I ask you to distinguish between 3 different substrates of benzene, which one will be ortho, which one will be meta, which one will be para, of the same compound, all you need to do is check out their dipole moment. The one with 0 dipole moment has to be the para disubstituted. The one with the ortho has to be the one with the higher one, while meta we have a lower dipole moment. So this provides a method to distinguish between the isomeric ortho meta para disubstituted benzene derivative. So dipole moment and ionic character. The magnitude of the dipole moment of a diatomic molecule determines its ionic character. So I can determine ionic character by knowing the magnitude of the dipole moment of a diatomic molecule. Let's consider hydrogen bromide molecule, whose measured dipole moment mu experiment is 0.79 dBi and the bond distance is 1.41 Armstrong. Don't forget, Armstrong is 10 raised power minus 10 meters. If the molecule were completely ionic, that means if the hydrogen bromide is completely ionic, each of the ions will bear a unit electronic charge. The electronic charge of each of the units, if it is completely ionic, the unit charge will be 4.8 times 10 raised power minus 10 ESU. This is a standard figure. Thus, the dipole moment of the ionic molecule can be calculated. So the dipole moment of the ionic molecule will be E times R, where your E is your charge, of course, which has been given to you. The electronic charge will be this times your R, which has also been given to you as 1.41 Armstrong. 1.41 Armstrong is same thing as 10 raised power minus 10 meters or 10 raised power minus 8 centimeter. So if I put that here, I'll get my value in dBA. You must use centimeter if I give you the unit in ESU. If I give you the charge in ESU, then you must calculate this one in centimeter. So, but the experimental dipole moment, mu experiment of hydrogen bromide, which determines its actual fractional ionic character, is 0.79. Don't forget that has been given in the question. Therefore, the percentage ionic character of hydrogen bromide will be the mu experiment over mu ionic times 100. So if I do that, 0.79, which has been given to us, divided by 6.77, which we calculated, times 100 is 11.6. Hence, hydrogen bromide is 12% ionic in character. So you can just approximate this to 12%. Can you see the way I came about this now? So in the question, you'll be given the experimental ionic character. Is that okay? And then you'll be given the charge, you'll be given the distance. Don't forget our mu, which is dipole moment, is equals to charge times your R, which is distance. So both of them will be given to you. If I give you the charge in coulombs, if I give you the charge in coulombs, then you can calculate you can use meters to calculate for your distance. But when I give you the charge in ESU, you must use centimeters for the distance. So by the time you multiply it, you get your value in dBA, and then you use this formula to arrive at your percentage ionic character. Thank you so much for listening.